Hi, good morning, everyone. My name is Guna. So thank you all for joining. A very warm welcome to all of you who have taken the time to join us today. So I'm really excited. This is the fourth micro workshop in our ongoing series of workshops. We completed 3 workshops in January and close to it was attended by close to 500 to 600 people in total. So, the amount of enthusiasm for these workshops is it is incredible. So we're very happy about that. So the fourth workshop, IIT Kanpur has graciously accepted our invitation to host this. Thank you, IIT Kanpur. The goal here is really to update the audience on all the work that's going on in relation to contributions that's going on into 3GPP, all the different work items. In the next couple of hours, you will see content from various experts talking about a lot of incredible topics: intelligent reflective surfaces, network architecture going from cellular to cell-free, smart nodes evolution, positioning framework, and so on. And each speaker will spend about 15 minutes on the topic, and the goal is to give you an overview of the topic itself. And if you find the topic exciting, and if your company is working on this particular area, or if you want to contribute in this area into 3GPP, work with TSDSI, or if you're not even a TSDSI member and you want to become a TSDSI member, for any of those reasons, we welcome you to reach out to us and have a conversation, and so that we can work with you on how to take you to the next level there, right? So, so without further ado, let's go to the next slide there. So I'm excited to introduce our first speaker of the day, Professor Ajit K. Chaturvedi. He's a professor at IIT Kanpur. He has held the positions of Sanjay and Rachna Pradhan, Chair Professor, Head of the Department of Electrical Engineering, Dean of Research and Development, and Deputy Director at IIT Kanpur. He was the coordinator of BSNL IIT-K Telecom Center of Excellence, which has done several projects for the Indian telecom sector. He's also a founding member of TSDSI, and he's also a recipient of INSA Teachers Award, Distinguished Teacher Award at IIT Kanpur, and Tan Chin Tuan Fellowship of Nanyang Technical University, Singapore. So thank you for joining us today. It's our privilege, and let's let you talk about this exciting topic today. Thank you.
Thank you, Guna, and thanks to TSDSI on behalf of IIT Kanpur for partnering with us to deliver this micro workshop, fourth in the series. Hopefully it will attract more people to this very exciting area, and hopefully many of them would like to partner with IIT Kanpur in different capacities. The brief outline of this talk is, first we will talk about what is this new notion of a programmable wireless environment, and why do we need for such a scenario to emerge. We'll then introduce smart radio environments, and we will show the roadmap for that, a very conceptual roadmap. Subsequently, we'll be talking about some hardware levers. So how such pieces of hardware have come into existence, which can be used very judiciously so as to achieve the goal of programming wireless channels. And when I say programming, what essentially is meant is that they can be customized as per the needs of a user in real time. Then we will put all the pieces together and say that all this is achieved thanks to the intelligent reflective services, or what we say as reconfigurable reflective services, intelligent services, RIS or IRS. And I'd like to end this very brief presentation by pointing out both some gains that have already been shown in simulations, as well as some challenges, so that we can integrate and assimilate IRS in future standards, cellular standards with 5G and beyond release 19, release 20, or even beyond standards, how they can be used. Next. So here I have shown a figure. This figure has been taken from a paper. The reference is given at the bottom. So all the figures we have given the reference at the bottom. It is trying to show users, 5 different users with different requirements. For example, user A and user D, both of them are interested in maximizing their signal to interference plus noise ratio because they want the best possible channel so that they can have the maximum download speed, best video experience. That is the kind of requirement that they have. On the other hand, if you look at user B, then user B is different from A and D in the sense that it is trying to do wireless power transfer. It is not interested in data transfer. So naturally, what will happen is that it is not interested in the multipath profile or the power delay profile of the channel that it is encountering. So that is the difference between the user pairs A and D versus user B. User B wants only power, but without any PDP concerns. PDP stands for power delay profile. On the other hand, user C is a user who just wants that even though he's operating in a wireless channel, he should get a private line to the base station. Private line in the sense as if there is a fixed wire and nobody can eavesdrop on his communication. So that is why we have used the word private air route. And user E is unauthorized. So we want that if user E is sending any transmission, then the environment should do something so that all the transmissions are blocked. He should not be able to interfere with the communication, neither should he be able to eavesdrop. Now, this kind of scenario is something that is not very far-fetched, something that we are already experiencing. Now it is up to us how to deliver it. Next slide. So in that sense, up to 5G networks, the paradigm was that how we can modify transmitter and reception schemes by using sophisticated algorithms so that we can get the best possible out of the given wireless channel. Now the paradigm is that let us not assume that the channel is something that cannot be changed or modified. In fact, we need to engineer the wireless channel so that it is programmable. So in that sense, there is a big philosophical shift, or shall I say, an introduction of a completely novel concept. Next. So in terms of a conceptual diagram, the diagram at the top is what has been used up to 5G, while the diagram at the bottom, or the second figure on the slide, is what we are going to visualize in beyond 5G and 6G networks. Major difference between the two figures is that in the bottom figure, you will see that there is a dotted red line that is connecting the oval shaped joint optimization with the wireless environment. We are calling the wireless environment as H because it is typically used as small h in the literature. And these two dotted lines that you see connecting the optimization problem with the wireless environment, they are back and forth. That means the joint optimization will not only learn from the environment, but will also modify the environment. That modification is present up to 5G. So that is why in 5G, the blue dotted line that you see, it is only one way. It is coming only from the wireless environment to the joint optimization problem. So we can say that the vision is to turn the wireless environment into an optimization variable so that just like the transmitters and receivers, it can also be controlled and programmed rather than just adapted to. Next. So these are the levers, hardware levers, I call them as, which will help us in realizing the dream of a programmable wireless channel. Because in the first, for example, the first one is reflection. So reflection means that traditionally we have been taught since our high school days that the angle of incidence will be equal to the angle of reflection. Now there is technology available by which it is not necessary that these two angles are kept equal. They can be different. Similarly, in the case of refraction, in the case of absorption, in the case of focusing, in the case of polarization, in the case of splitting, splitting means that there is one incident wave, and from that one incident wave we have created multiple waves. Analog processing is that there is an incident wave and the output wave is either a differentiated version of that or an integrated version of that, and that processing is not done in the digital domain, it is done directly on the wave. And collimation is of course the converse of focusing. That means it is coming from one point, but then it is being sent as a parallel in a particular direction, not at a point. Similarly, you can see that there is this absorption. All these are elementary EM wave operations. So absorption is that there is an incident wave, but then nothing is getting out of that. So if we can achieve these blocks using some devices, then naturally it will become very close to what is called as a programmable wireless channel. Next. So here we have shown the real engineering that has been done, and it is using what is known as meta materials. Using meta materials, meta surfaces are created. So what happens is that it consists of static meta atoms and dynamic meta atoms. So the static meta atoms, whatever the current that flows on these on the surface is completely dictated by the geometry of the static meta atoms, and of course also on the material. That means which meta material has been used. On the other hand, in the case of dynamic designs, that is dynamic meta atoms, there is also a switching matrix. So using the switching matrix, it is possible to alter the current that will flow on the surface and accordingly the response field. Next. So this is putting all the layers together of an intelligent reflective surface. This was the title of the talk. So now we can see the first conceptual diagram of what is an intelligent reflective surface. So there is a control plane, then there is this what I talked on the previous slide, that is the dynamic and the static meta atoms, and they are used to constitute what are known as square patches, which are passive, and switches, which are active. So the square patches, that is on the green layer, they are basically passive, so they don't consume any power. On the other hand, the switches, naturally they consume power. Even simple mechanism of on-off switches are sufficient for building surfaces which support an impressive range of electromagnetic functions. That means what I mentioned earlier, like focusing or absorbing or phase shifting or reflecting or refracting. Next. So here the complete picture is shown now at one place. So there is it is like IRS is like a wallpaper, just like we put walls on our rooms or buildings. Similarly, the future is that our ceilings or walls or on buildings will have some kind of a wallpaper which is composed of very cheap, very inexpensive composite material, and it is capable of modifying the radio waves. At the bottom you can see that there is a dotted line within which there is a processing unit, there is a microcontroller, and there is an optional radio frequency chain. Of course, some kind of radio frequency will be required to be able to control the control information, but usually there will not be a separate RF chain for IRS, because it will not be generating its own radio waves, neither it will be amplifying radio waves. Next. So these are two pictures. We are showing these pictures of real prototypes. One that has been developed at NTT Docomo, that is on the left side, and the right one has been fabricated at MIT. So these are real intelligent reflective surfaces where metamaterials have been used, and they consist of thousands of cells, and each of these cells will have a switching matrix, and accordingly it can be programmed to be on and off, and that can be done dynamically in real time. Next. So now I'll show that how these intelligent reflective surfaces can actually be used to get gains in the physical layer. For example, the next three slides, they're all about the Noma network. In this slide, what we are showing is that as the channel estimation error variance increases, that means the quality of information that I have about the channel becomes inferior, the spectral efficiency goes down. But by using IRS with larger number of elements, I can compensate for that and improve my spectral efficiency. Next. This is in a similar context, Noma Network, we are showing that by using the number of increasing the number of RIS elements, we can reduce the transmit power required from the base station without compromising on the spectral efficiency. Next. Here we are comparing clusters of Noma and OMA settings. We have fixed a target spectral efficiency per user, and we have also fixed the variance of the channel estimation. And what we are trying to see is that as we increase the number of users, what happens on the transmit power. So it happens that if you have more number of users, naturally you need more transmit power, but then it is less in the case of Noma compared to OMA. And at the same time, even in the Noma and OMA both cases, by using more elements, I can reduce my transmit power. Next. So this slide covers what is the future of reconfigurable intelligent surfaces, the name that we have used for IRS, and in terms of what is the challenge ahead for the future releases, in terms of channel estimation, in terms of beam forming design, and in terms of co-channel interference coordination. Because if we can realize these things effectively, then what will happen is that the potential gains offered by this new technology will translate into gains on the ground. So for example, we know that the channel estimation overhead will be increased because now you have to do a channel estimation from the base station to the RIS and from the RIS to the user equipment. And so naturally the overhead will increase, but then we are also saying that because of millimeter waves and because sparsity will be there, and because we are hoping that it will be possible to use AI and ML techniques that are growing in parallel, by the application of these things, it should be possible to address these challenges and make this a reality. For example, in the case of beam forming design, we can see that the overhead required for each of the elements will be more, but then we see as a potential solution as robust beam forming design with CSI error models. So this is the, on the right hand side, we are showing that what is the possible solution. That means where to look for solutions. Of course, this is not exhaustive. These are just some suggestions that have appeared in the January 2023 issue of the Communication magazine. But then it is up to us, the research community and the standardization community, to make sure that we come up with algorithms which can address these challenges and make sure that what metamaterials have given us, we are able to make the best use of it. Next. Thank you. So with this, I conclude my talk, and I would welcome questions both in the chat box right now, as well as in the end when there is a time for that. Thank you.
Thank you, Professor Chaturvedi. That was wonderful. That was a wonderful talk. You were clear and lucid. Really appreciate it. Learned a lot about reflecting surfaces and the potential benefits. And it's a very promising area for further research and development. It also needs careful planning, it looks like. And so thank you again. Really learned a lot. So let's go to our next speaker. I'd like to give a warm welcome to Professor Rohit Budiraja, who's currently an associate professor at IIT Kanpur. He's currently leading the 5G and beyond standardization project at IIT Kanpur. And he also led the effort to design the indigenous 5G network. From 2004 to 2011, he worked for two companies where he designed from scratch both the hardware and software algorithms for WiMAX and LTE-based cellular systems. So welcome, Mr. Rohit, and I'll let you do your slides. Thank you. Please go ahead.
Thank you for the introduction. And so if you look at that today's 5G network, so they are basically have a cell. These networks are designed in form of cells, wherein there is a base station in each cell, and there are UEs or mobile stations connected to each one of them. So, and because of the scarcity of spectrum, the spectrum is reused in all the cells. So base station 1 and base station 2, they reuse the spectrum. For example, 100 megahertz spectrum, which is allocated to an operator, will be reused in all the cells. So what it leads to is something called the cell edge problem. Next slide. What happens is that a user which is located at the cell edge receives signal from both the base station. The reason being that is the signal is transmitted on the same spectral resource, the same frequency band. And if a signal is meant for user in cell 1, a user in cell 2 will also receive. So you see these signals being received by both the users which are located at the cell edge. And since these users are located at the cell edge, the signal and interference from both these base stations will be of the same strength. So the effective signal to interference ratio will be actually 1, and the desired mobile station will not be able to decode its signal. So in 5G, basically what has been done is that massive antennas have been used at the base station to reduce this interference. And what happens is that it helps in making small, very sharp beams towards the user. Next slide, please. So you look at it when we use massive number of antennas at the base station, and which are typically being used in release 15, release 16 networks, that it helps in forming very, very sharp beams towards the user. And as a result of that, this intercell interference, which basically the users were observing earlier and which was so strong for the users at the cell edge, it comes down. Okay. But the thing is that in order to form these smart beams, the base station requires accurate channel information, and which is in the standard community is well known that it is like it's a non-trivial task. Next slide, please. Now, what happens is that despite the large number of antennas being used in this 5G base station, the problem of the cell edge still persists. And though the interference reduces because of large number of base station antennas being used, it still persists. Plus, there is a lot of path loss when the users are at the cell edge. So if you look at this particular figure, wherein like a user which is located very close to the base station will observe a data rate which is as high as 80 megabit per second, okay, per user. These peaks show the data rate being observed by the users which are located close to the base station. As you move away from the base station, then look at the data rates, it drops down radically. Right, then from 80 megabits, it is reduced to 20 megabits. So there is the uniform service. So an operator is not able to provide a uniform service in the current 5G network also. That's one problem which operators have been facing. From 80 Mbps to 20 Mbps, this is a huge variation. So this current figure, which is taken from the reference, it shows these kind of bit rates for a 4-cell network. And if we extend it for a 64-cell network, we will see again a similar kind of variation. Next slide, please. You see this again, like the data rate, it is fluctuating from close to like a few Mbps to 80 Mbps, and which is not a nice thing for an operator, because a user located at the cell edge should actually be able to get the same kind of service which a user is located to the base station is getting. And because both the users are paying same amount of money, why should a user located far away from the base station should get a degraded service? So this is a real concern for the operators, and that's where new kind of architecture is being envisioned for release 18, 19, 20, and beyond. And this is what we are going to talk about in the subsequent slides. Next slide, please. So this is something called the Selfie Architecture, which is basically akin to distributed massive MIMO. So if you look at it, there are instead of one base station, there are like multiple access points now, which are basically low base station with lower number of antennas. Each access point, instead of having like 64 antennas or 128 antennas, it'll have only 4 to 8 antennas. But so many of these access points will now collaborate to basically transmit data to the users. So take an example of UE1. Now the access points, which are like shown in yellow color, they will collaborate to transmit data to user 1. Similarly for other users also. So you'll see that in fact there are like overlapping sets of access points which are transmitting data to different users. So different access points, they network together to transmit data. And since so many of these access points are serving a particular user, and there is no notion of cell now, you see that we are like a user which used to connect to a particular base station in a cell, that is not happening now. Okay, so and since there is a cell is not there, so the cell edge problem actually goes away. And we'll show you that how with the data rate which users are able to obtain now with this kind of a selfie network. Next slide, please. So you look at this. This is now the data rate variation is actually has come down radically. It is from 80 Mbps. It is now 60 Mbps, and it doesn't go down. So the reason being that is that the interference has come down because there is no notion of cell. A user is talking to multiple access points, and the notion of massive MIMO still remains, which helps in cancelling the interference, the intercell interference, because there are like a lot of access points, and each access point has like 4 to 8 antennas. So the intercell interference cancellation capability of this network still remains. Plus, there is an added benefit of a lower path loss because there are so many access points which are serving a particular user. So this helps us in mitigating this cell edge problem, plus helps an operator in providing a uniform quality of service to all the users in the network. Next slide, please. Now, what is the challenge in this selfie network? There are multiple challenges, but I would like to focus on one challenge, which is basically sharing of the channel state information across these access points. As we discussed in the beginning of this talk, that in order to form these sharp beams towards the user, the base station needs channel information. And now there are multiple access points which are serving a particular user. So all these access points need to know this channel information. So how is that achieved? That's what we are going to discuss briefly in the subsequent slides. Next slide. So this is a picture of the 5G network which we have designed across multiple institutions. And if you look at it, the way it is architected, and this architecture will actually facilitate the implementation of a selfie network also. So there is a remote radio height which basically transmits the signal. There is, and it up converts, down converts the signal. Then there is something called baseband unit, which is the heart of the network, which does the complete processing. It runs like physical layer, it runs the upper layer, MAC, RRC, it runs all these layers, and finally it is connected to the core network, which does, with, for example, billing authentication. So this is how these current generation 5G networks are being designed. Next slide. So this is how now the earlier I showed you a schematic of one of the base station. Now if you have to connect multiple such base stations, the architecture is scaled as follows. Next slide. Next slide. So you look at it, that there are like, if there are 3 cells, so basically the data of all these cells is being brought together to this baseband unit, and which does the complete processing for all these base stations. So each such, so it is like basically a cloud wherein the processing for all these base stations is being outsourced, and this computing cloud is basically co-located at a centralized place, and the data from all these remote radioheads are being brought together from using these optical interconnects. So you see that the processing is actually already happening in a centralized place in these 5G networks also. Okay. So next slide, please. So now this kind of centralized architecture enables us to basically share this channel state information, and so it becomes easy because the data for all these base station is coming to a centralized baseband unit which can share this channel information. So even current generation 5G networks are being designed, though they were not designed keeping the Selfie architecture in mind, but it so happens that they can also enable this kind of architecture. It's just that now to enable this Selfie architecture in a true way, these access points will have to be like designed such that they are low cost, have low number of antennas, and there are so many of them. So all these access points, they'll have to basically come to this centralized processing unit, which will share the channel state information across each other, and then finally they'll be connected to the core network. So this is now keeping this 5G architecture in mind. This like the Selfie architecture is also looks similar to the way we have designed this 5G network. Next slide, please. So this Selfie architecture appears mildly in release 18 and release 19, and this is given a name as a coherent joint transmission. So what is happening here is that 2 base stations, by assuming ideal backhaul and synchronization, they can like jointly serve a particular user. So if you look at this diagram, that you can assume that these 2 nodes, the base station nodes, they can like cheap nodes with fewer number of antennas. They are serving a particular user, and user is basically sharing the channel state information. The PMI is the quantity, or is the information which is shared by it. It's the kind of channel state information. So the precoder matrix indicator, which is shared by the user across these base stations. And this is already happening, and we believe that it will continue to evolve in the future releases also. Next slide. So the conclusion is that the Selfie architecture, it provides uniform quality of service to users in the network. And this is, we discussed also that with this architecture, the data rate actually doesn't fluctuate much, and which is a boon for the operators, because they can assure this kind of service and then a uniform service, and it's actively being considered for release 90, and it'll evolve. The architecture will evolve for release future releases also. Next slide. Thank you. This is what I had to tell about the Selfie architecture, and I'm sure there are like I pointed out one problem. There are multiple such problems which are waiting to be solved. Thank you.
Thank you, Professor Rohit. That was wonderful. I guess I have to say thank you twice, because you also finish exactly on time. So that's another great thing. So definitely an exciting field, and has the potential to significantly enhance the performance and efficiency of 5G. I mean, The cell edge problem is something that people have been struggling with for a long time. So this is indeed music to my ears. I mean, advanced technologies like massive MIMO, distributed processing, definitely can improve the scalability big time. So, and also there are challenges and there are plenty of work to be done. So if any of you watching this find this to be interesting, exciting, please reach out to us. We'd definitely like to talk to you for direct contributions or collaborations or any of that. And if you have questions for Professor Rohit, put it on your chat box, and we will get to it. And if possible, towards the end, we can probably answer it live, but we'll definitely get back to you in the chat line. So thank you, and let's go to our next presentation. And I'm happy to introduce our next speaker. Mr. Shyam Vijay Gadai is currently working as Project Executive Officer in 5G plus 6G research and standardization project at IIT Kanpur. He is a 3GPP RAN 1 delegate contributing to Release 18 network control repeater. His research interests include MIMO systems, smart repeaters, reconfigurable intelligent surfaces, which you heard before, integrated sensing and communication. So welcome, Mr. Shyam. So I'll let you go through your presentation. Thank you.
Yeah, thanks a lot for the kind introduction. I will be describing about evolution of the network nodes, which have been continuously evolving since some few generations. So first, let's look at conventional repeaters, also known as RF repeaters. So these have been used since last couple of generations to increase the throughput, or basically enhance the coverage of the base station or a cell, which Professor Rohit Budiraja introduced last. So a repeater basically just amplifies and forwards a signal. Now, this node does not have any intelligence or does not do any processing or decoding. Hence, it does not have any information about any directions about the users to broadcast. So typically, it's an omnidirectional broad beam, which it does. And if we look at the current evolution of the frequencies, that is, we are going towards the millimeter wave frequencies and beyond. So for them, the path loss is huge. And in that scenario, such repeaters have less coverage. Similarly, because they also have an omnidirectional broad beam, they can interfere towards different users or towards users of other cells. Also, as they don't have any control over themselves dynamically, so they always remain on, and the power wastage is much higher with these repeaters. Next slide, please. Yeah. So recently in release 18, a new node was introduced, which is known as network controlled repeater. So this is a smarter version of the RF repeater. This one also just amplifies and forwards the data. However, it has the capability to get some information from its parent base station or a node which is controlling it, and it is able to beamform towards dedicated directions. It can manage its downlink and uplink transmissions. It can also switch itself on off. This is possible because of a site control information which is sent from the base station to the repeater, and the configuration and signaling of this NCR or network control repeater has been done in release 18. Next slide, please. Yeah, so I will briefly just describe about the architecture of NCR so that we can understand it from standardization point of view, and going forward, new nodes which can be introduced. This NCR has typically two units. One is NCR empty and other is NCR forwarder. The NCR empty usually works as a UE only with respect to base station. It needs to decode a control information, and this control information is only for the repeater. It's not any control information intended for the UE. Now, to have such decoding capabilities, there is a layer 3 protocol level kept there. So it has protocol stack also, similar to GNodeB it has. However, this protocol stack is only used for the control information for the repeater itself. Hence, it does not interact with the data or control to be forwarded to UE, and hence it does not directly interact with UE. That is, the UE is not aware that there is a repeater in between. It only knows that there is a base station. Hence, in this way, it is different to a GNodeB, and its main function is that of forwarding. So the NCR forwarder unit will typically forward the data to and fro between the GNodeB and UE. So this is hence this control link, backhauling, and access link that you see. So what signaling has to be done for controlling, how the configuration will be there for the NCR empty, NCR forwarder, etc. All of this has been standardized in release 18 of this NCR. Just for the information that this NCR started as a study item in release 18, and now it has converted to a work item, and now it's to its completion. So the NCR will now just get completed in the next meeting in March, and the complete specification will be finalized after that. Yeah, next slide, please. In this release 18 NCR, there were some constraints imposed on this device, that it has only to be a single hop device, which is that between base station and UE only a single device is kept. It's a stationary device, it does not move. The control and the forwarder links are in-band, that is, they work on the same frequency band. So such a basic model was agreed in release 18. So for the release 19, there is a strong possibility that enhancements on NCR can come up, and it can be introduced as an item where all the constraints put, such as a single hop, stationary, all can be moved to its enhanced version. Like there can be multi-hop deployments, mobile NCR, such as vehicle mounted repeaters, multi-band operation between the controlling and forwarder link, many other enhancements like feedback enhancements or capability enhancements, which the repeater can provide to the base station, etc. So these are not yet introduced, and there is a strong possibility that if a repeater based item comes up in the release 19, these are the enhancements which can come up. Moving on, next slide, please. Yeah. So Professor Ajit Chaturvedi previously introduced the reconfigurable intelligent surfaces. So these are also the new nodes or new network nodes which can be standardized. I won't go into detail of RIS, but just that it's a passive antenna element device, and this can also work for enhancing the coverage or removing the blockages in the cellular networks. Yeah, and next slide, please. Yeah, so let us see what differences will RIS have as compared to the NCR, because they are all the network nodes which are used for enhancing the coverage and the throughput. So as seen in the figure also, so basically a repeater or this NCR will have two antenna panels, one towards the backhaul direction and one towards the access link. It has up to layer 3 protocol stack, as we saw before, for the control information. It definitely has the complete RF chain as it needs to amplify and forward the data. The beam weights which need to be provided are for both the transmitting side and the receiving side. And as well, because it has the power control information, so it can manage interference. That is, it can direct its power more towards the intended direction and reduce the power towards unintended direction. Now, if we talk about RIS in this aspect, then the RIS will only have a single, basically a meta surface or a panel is there, and there is no protocol stack envisioned to be there. Definitely, there is not going to be any RF chain, and in the literature or the theoretical literature, there is a talk about that RIS can have active antenna elements or passive antenna elements, and there are mixed architectures available. However, considering that smarter version of repeater, that is the NCR, which has active antenna elements and it can beamform, has already been standardized, the most probable way a RIS will be standardized will be via just passive elements. That is, it will have just passive phase shifters which can beamform. and only a single set of beam weights for a single panel need to be provided, and they have to be designed such that they can cater to the best directions both for the RX and TX. However, it won't be having any power control there, so interference management is one issue, and some procedures related to that can also be standardized. So next slide, please. Yeah, so in this I will describe in detail like what scenarios can be done for the standardization of this RIS. Now, in release 18 workshop, many companies did try to push the RIS for the standardization. However, it was not agreed at that point. So we think that again in release 19, other companies may try to push, and there is a strong possibility for release 19. And if not release 19, definitely the future releases where RIS can be standardized. So these are some aspects which need to be taken into account, like the use cases or the deployment scenarios, in which scenarios these RIS can work beneficially. Such evaluations can be done. Then the current existing channel model, which has been agreed in 3GPP, can be modified by integrating RIS into it, because RIS can work as an integrated a node or a cluster inside the complete channel, and its different effects of near field and far field of the channels and other path loss and many other things related to channel modeling can be studied and evaluated. Then definitely the architecture of the RIS itself, whether having what should be, how large the RIS should be, what elements it should have, etc., can be standardized. Further, as the main property of this RIS is beam forming towards the intended direction, hence the existing procedures in 3GPP for beam management, such as beam sweeping, beam failure detection, beam failure recovery, etc., how do they change, or is any change needed for them, can be evaluated. Similarly, previously, as I mentioned about the interference part, that it does not have any power control. So the interference management related procedures can again be standardized. So these are some aspects on standardization of RIS. Next slide, please. Yeah. So here I will talk about RIS for integrated sensing and communication. So in this integrated sensing and communication is basically a dual job, which is common base station can perform sensing as well as communication. And sensing is basically mapping or getting information of the complete environment in which the communication is going to happen. So this ISAC has already been started as a study item in release 19 system aspects group. However, for the RAN group, the release 19 is yet to come. I will describe it in the last slide, the timeline for it. But this ISAC based systems require the complete sensing of environment, and RIS can assist in them. So now, because this ISAC system will require a different signals for sensing and communication, and if, as this is a part of release 19 assay, and if it gets standardized, how RIS can assist in them, or what changes are needed for the signaling to enable ISAC can be studied from RIS perspective as well. Similarly, the next slide, please. Yeah. Similarly, there is a positioning framework going on in the standardization. So positioning is nothing but knowing the location of user devices or target devices. Now, this positioning evolution framework has been continuously evolving since some generations, and it is still evolving and will go on for the next releases. So when RIS comes into picture, what is the configuration and signaling needed for such enhancements of high accuracy positioning or very reliable positioning can again be studied, and the configuration needed for that, any new signaling needed, can again be studied from that perspective. So this is how these new network nodes which are being introduced, like repeaters, RIS and all, will help towards the use cases of next generations. Also, as previously Professor Rohit Budiraja mentioned about the cell-free architecture. So these network nodes will help to evolve from cell-based to cell-free architecture now. Next slide, please. So I will just finally give the audience some timelines that have been agreed in 3GPP. So for the RAN, that is the Radio Access Network based group in release 19, a workshop is going to be held in June. And by the end of this year, 2023, the release 19 package will be approved, and the RAN 1 work on release 19 will start from the next 2024 starting quarter 1. So we wish that more people from Indian uh, country here can contribute more to the release 19. Yeah, so that was it from my side. Thank you.
Oh, thank you, Shyam. That was come on. Thank you, Shyam. That was wonderful. Another definitely exciting topic. I mean, it's nice to see all these things which are actually going to dominate the conversations going forward, and the users, the audience got a front row seat in purview on what is going on. So really appreciate it. I mean, network control repeaters is a personal favorite of mine. I think. They have a potential to severely bring down the cost of the RAN, right? Because in combination with G-Node Bs are quite expensive, right? So,
Mm.
I mean, you definitely can, instead of just putting pure G-Node Bs, you can put a combination of G-Node Bs and NCRs, and
Correct.
you can bring down the cost of a RAN deployment big time, right? So,
Correct.
and thank you for talking about the release 18, release 19 timelines and mentioning that, because we, if you look at the number of contributions that's coming out of India, we are still, we're still not at a very high level, right? We're probably about 0.5% of the total contributions going into 3GPP.
Correct.
And so we definitely need more people coming into the standardization path, come into contributions, collaboration, work with us on all those new exciting areas, right? So you could see that there is plenty of new potentials for company products, new IP. You can do standard essential patents. I mean, the opportunities are endless, right? So, anybody could be in the audience who's going to be the next big telecom equipment manufacturer coming out of India, probably, right? So that's our goal. So we need a lot of people, a lot of companies who are reaching a unicorn kind of status, right? So thank you, Shyam. That was definitely eye-opening. Appreciate it. As usual, audience, if you have any questions for Shyam, please put it on the chat box and then mention his name so that we can get to it, and we can probably towards the end, but looks like all the speakers are staying on time, which is amazing. so we are definitely on track. So let's go to the next speaker. So Jyotirmay, warm welcome. Happy to introduce you. Mr. Jyotirmay Saini is currently working as Senior Project Engineer in the 5G plus 6G Research and Standardization Project at IIT Kanpur. He is contributing to the positioning framework in 3GPP, which is another very important area, as a RAN delegate. His research interests include localization and sensing, repeaters, reconfigurable intelligent surfaces. So a lot of RIS work going on in IIT Kanpur, looks like. So I'll let you get into the content. Thank you.
Thank you for the kind introduction. I'll be talking about the evolution of positioning framework in 5G. Next slide, please. Yeah. So previous speaker actually introduced positioning. Thank you, Shyam. So positioning is determining a user or device location, also known as localization. There are n number of enablers and technologies which could help you estimate the position. So when we use cellular network, that comes under the category of RAD dependent technologies. And when we use technologies like GNSS, Wi-Fi, Bluetooth, which are not the part of cellular framework, that comes under the category of RAD independent technologies. Moving on, we'll discuss popular approaches of finding the position of a target device. Next slide, please. So first one here is trilateration. So it's a distance-based approach where we find the distance of a target device or a user with respect to the network node. Generally, this distance is estimated in terms of time of signal traveled in the air. There are measurements like time of arrival, time difference of arrival, multiple round trip times. These every measurement has pros and cons in terms of signaling overhead and the robustness against network synchronization errors. Next slide, please. Yeah, there is another technique called triangulation. It's an angle-based approach where we try to find the orientation of the user with respect to the network node. So when we estimate the angle of signal transmitted by the network node towards the UE, it's called downlink angle of departure. And when we ask user to broadcast the signal, and at network nodes we try to estimate the direction of arrival of the signal, it is called uplink angle of arrival. Apart from directly getting directly estimating the angles, we can use signal strength to know the direction of a user with respect to the antenna node, and using this direction information we can estimate the position. Next. So now we will talk about positioning enablers in 5G. So 5G technologies are uniquely positioned to provide added value in terms of enhanced location capabilities. The operation in low and high frequency bands like FR1 and FR2 and utilization of massive antenna array provides additional degree of freedom to substantially improve the positioning accuracy. The possibility to use wide signal bandwidth in FR1 and FR2 brings new performance bound for user location for well-known positioning techniques utilizing timing measurements to locate UEs. Apart from that, the recent advancements in massive MIMO systems can provide additional degree of freedom to enable more accurate user location by exploiting the spatial and the angular domain of propagation channel in combination with the timing measurements. Now, in subsequent slides, we will talk about the positioning from the 3GPP standard perspective. Next slide, please. So positioning, or I will say standalone NR positioning was introduced in release 16 to meet the regulatory and commercial requirements. In release 16, we defined new reference signals specifically for the purpose of positioning. We defined new radio resources to enable positioning. And apart from that, we worked on a standalone NR positioning protocol in release 16. So release 16 positioning features were able to give us less than 3 meters of accuracy in indoor scenarios, and we were able to achieve less than 10 meters of accuracy in outdoor scenarios. But these requirements were not sufficient for 5G service requirements for applications like industrial IoT. So for example, in a factory setting, you need to monitor or keep the track of moving objects like forklifts or a part to be assembled. Or similar requirements are there in logistics and transportation industry, which needs higher accuracy and lower latency, which was not supported by release 16 features. To the next slide, please. Yeah. So to cater to these high accuracy and low latency requirements, in release enhance the legacy features, and we were able to achieve sub-meter level of accuracy in release 17. Apart from that, we were able to substantially reduce the position estimation time to less than 100 milliseconds and advancements on physical layer procedures, we were able to do the positioning measurement itself in less than 10 milliseconds. With this, we were able to cater to the industrial IoT scenario. Can we go to the next slide, please? Yeah. Now the standards group is currently working on release 18 positioning features. So, well, I'll talk about the enhancements we are doing in the release 17 features in terms of accuracy, power consumption, and integrity. From integrity, I mean the reliability of the measurements reported by the devices and the network nodes. Apart from that, to increase the accuracy, we are working on supporting ultra-wideband positioning using carrier aggregation. And apart from that, we are introducing a new measurement altogether in positioning framework called carrier phase measurement, which will help us to achieve centimeter level of accuracy. To enhance or to make the positioning framework power efficient, we are doing the enhancements in signaling to achieve low power, high accuracy positioning. So these were the few enhancements we are doing in the legacy features. But apart from that, the group is working on 2 additional features called positioning for RedCap devices and position support for saddling. We will talk about them in the coming slides. Next slide, please. Okay, so here you can see the 5G in the figure. The 5G was envisioned and designed to serve unprecedented range of capabilities with a single global standard, with features like enhanced mobile broadband, massive machine type communication, and ultra reliable low latency communication. But in release 17, 3GPP introduced a new tier of reduced capability RedCap devices, also known as NR Lite. It's a new device platform that bridges the capability and complexity gap between the 5G extremes. When we compared these RedCap devices with conventional 5G UEs, they operate at narrower bandwidths, that is 20 megahertz in frequency range 1 and 100 megahertz in FR2, frequency range 2. They generally support a single transmitter antenna and receiver antenna. They operate at lower modulation order. They support low transmit power. So this reduced complexity contribute to the more cost-efficient NR Lite device and the longer battery due to the low power consumption, and the smaller device footprint, which enables a new design for the broad range of the use cases. Now I'll talk about the challenges brought by these constraints actually. So when we talk about a device which is operating at lower bandwidth, the positioning measurement accuracy actually decreases, which makes it hard to achieve the desired positioning accuracy. So currently, the group is working on enhancing the physical layer procedures or defining or enhancing the physical layer reference signals to achieve the desirable performance for RedCap devices. Next slide. Yeah. Now coming to the side-link scenario. So side-link is a network topology where a device is communicating with other device without the participation of the base station. Side-link was introduced in release 16 of 3GPP standards, but now in release 18 we are extending the positioning support for that. We are defining new position. We are actually defining a new protocol itself for the new link. Apart from that, we are doing side link specific physical layer procedure development and reference signals to do the positioning on the side link. So that is going on in release 18. Going to the next slide, please. Yeah. So before I talk about the future work and use case, future work and standardization aspect of this work, I would like to take some time to introduce the new KPIs and use cases we may need to cater with release 19 and beyond for positioning. So we need wider coverage, we need high range resolution, we need extremely accurate positioning. Apart from that, we need ultra low latency positioning. Although we support low latency positioning, but we need to go to ultra low latency to cater to the future requirements. Apart from that, we need high availability and high scalability. So let's talk about the use cases like high speed mobility and extended reality. So these are the two use cases where, along with the accuracy, you need ultra low latency, because suppose you have a high mobile UE, till the time you estimate the position, that information will become obsolete because the UE would have moved substantially. Or when we talk about mission critical applications like collaborative robots or autonomous vehicles, along with the ultra low latency, we need high availability. So from availability, I mean making the service or meeting the performance for 99.99% of the users. Currently, we have the availability of 90% only in the existing framework. Next slide, please. Now I'll talk about the standardization aspect for release 19. So the extension on release 18 features, we can support side link in FR2, which is not supported in release 18 work. In release 18, we enhance the definition of RedCap devices for the UEs operating at 5 megahertz. So as we talked earlier, if you decrease the operating bandwidth, the accuracy of measurements reduces. So how do we achieve the performance with the constraints? When you talk about increasing the accuracy in 3-dimensional space, so when you talk about UAV, which is a UAV not only moving in the horizontal plane, but also moving in the vertical plane, we need to increase the accuracy in 3 dimension. And we already talk about the availability. We need to go beyond 99%. Apart from that, there are two new use cases or new features we need to include in release 19, that is architecture for ultra low latency positioning. And we may need to extend the support of positioning for unlicensed bands, especially for extended FR2, where the frequency will be in terahertz, which could serve as a stepping stone towards 6G localization and sensing. Next slide. Next, thank you. So I'll quickly talk about the challenges for release 20 and beyond. With 6G, new physical layer procedures and new technology will come. To cater to those, we need to have more calibrated hardware impairment models and channel state models. Apart from that, we need to improve our coverage. So previous speakers talked about IRSs and network nodes, how to exploit them to achieve higher accuracy in positioning. So suppose we can use IRSs and make them virtual nodes to gather more information to give you better quality of service in positioning. We need to enhance the accuracy. So for sensing purposes, we may need to introduce a new signal, or we may need to study the feasibility of the existing waveform for the sensing applications. And for the applications like tracking, we may need to use AI/ML to reduce the signaling overhead. Next slide. Yeah, so with this, I would like to conclude my talk, and I would like to say that there is a substantial amount of work to be contributed in positioning framework. I would like to see more contribution from Indian IEMs in 3GPP standards. Thank you very much.
I think that was a wonderful talk. I really appreciate you going through this another exciting topic. Definitely exciting because it combines the power of 5G and industrial IoT, and you know, there are plenty of use cases for something like this, right? Navigation, even asset tracking. I don't know whether it probably needs some very, very small kind of resolution, right? I'm not sure we'll get there, but emergencies, vehicle-to-vehicle navigation. I mean, definitely another very exciting area. So thank you for taking the time, and let's go to our next presenter, please. Thank you. So our next presenter, I'm excited to introduce Ms. Asna Kumari. She's currently working as a senior project engineer in 5G plus 6G relevant research and standardization project at IIT Kanpur. Our research interests include MIMO evolution and study of possible new waveforms for the next generation communication systems. So without much further ado, I'll let Ms. Asna take over. Thank you. Asna, are you there?
Yes, sir. Sorry, I forgot to unmute.
Yeah.
Good afternoon,
Please go
everyone.
ahead.
So my topic of presentation today is new waveform design. Next slide. New waveform design topic has been included in 3GPP under the title NR operation extended to 71 GHz. In plenary 16, it has been decided that spectrum band 52.6 GHz to 71 GHz will be included in release 17, and above 71 GHz spectrum band has left for the future releases. But in release 18 study item, there was no discussion upon this topic. So we are anticipating that this topic is going to be introduced in release 19 and beyond in 3GPP standards. Next slide. So why we need to go beyond 71 GHz? So there is various application and requirements of 6G where we need very large bandwidth and ultra wide and contiguous band, and 71 GHz spectrum has the potential to fulfill those requirements. Also, it offers extreme capacity for short range use cases, and sub-terahertz band provides excellent property for sensing and imaging. So it is a very strong candidate for a key technology in the next generation communication system, that is integrated sensing and communication. 6G is going to include all the spectrum band from the previous releases along with the sub-terahertz band. Next slide. So there are few challenges in high frequency band, like the power amplifier efficiency reduces due to non-linearity, and the phase noise increases, and the effect of Doppler spread also increases in high frequency. Like in this table we can see, for the velocity of 5.5 km per hour, for given carrier frequency 2 GHz, we experience 10 Hz Doppler spread, but for carrier frequency 60 GHz, we experience 300 Hz Doppler spread. So while increasing the carrier frequency, the effect of Doppler spread increases. Next slide. So why do we need a new waveform? With the increasing challenges in the higher frequency band, the current CPU FDM suffers in a few scenarios, like due to it is a multi-carrier modulation scheme, so it introduces high PAPR, and power amplifier is already giving very reducing the efficiency, so the overall link efficiency reduces. Also, FDM is not very robust against the phase noise. It is well known that OFDM does not perform very well in high Doppler spread scenario because the orthogonality of the subcarriers is compromised after a very high time varying channel, and the equalization becomes very difficult. So the performance degrade in case of high Doppler spread. So there is a requirement of new waveform which can provide robustness against these challenges of a high frequency band. Next slide. So there is a waveform, orthogonal time frequency space. Here I'm going to explain in detail about this waveform. Next slide. OTFS has introduced a very unique property of channel model. It introduces the channel in delayed Doppler domain, whereas the technology till now model the channel in time frequency domain. Here is one example I want to explain. Delay axis mainly introduces the delay provided by the reflector between the transmitter and receiver for the NLS link, whereas Doppler is going to give the velocity of relative velocity with respect to the transmitter and receiver for that link. For example, if we take the building scenario, the building is at the lower end of the Doppler spread and also at the lower side of the delay. It is not zero in the Doppler axis because UE has some velocity. Similarly, for the car and drone example, we have velocity at the higher side, so it is placed at the higher end of the Doppler axis. Next slide. We can translate from delay Doppler axis domain to time frequency domain, where Doppler is related to the time with inverse Fourier transform, and delay is related to the frequency with the Fourier transform. Here we can observe that the channel model in the time frequency domain is very dense, whereas in delay Doppler the channel is sparse, because in delay Doppler the channel basically captures the parameters due to that particular reflector, and here the characteristic is localized in delay Doppler domain. Here delay and Doppler are not directly related to each other, but time frequency domain is related to each other with the Fourier transform. So when a particular channel model for a particular reflector in delay Doppler is translated to frequency domain, it spreads over the whole time and frequency spectrum. So here we are going to experience a dense channel model, whereas in delay Doppler we have sparse channel model. Next slide. Here is another example. So we can see in delay Doppler the channel parameters are very sparse, whereas in time frequency it is dense. Here the blue color car is our receiver, and the transmitter is at the roof of this bus stand, and we observe this particularly yellow line reflector, which is car is circled in red color. So at time instant t0, we have 4 reflectors, and when we observe at time instant t0 plus delta, we increase the velocity of this car. So what happens, only the channel parameter related to this yellow color line changes in the delay Doppler domain. Other parameters related to other reflectors remain same. Whereas in time frequency domain, we observe that there are various changes in the parameter of time frequency. So OTFS channel model provides a slow variable channel model. Next slide. OTFS is implemented by introducing a pre-processing and post-processing block in the existing OFDM modulation. In OTFS model, the symbols are mapped in delay Doppler domain, and in this pre-processing block, what actually happens is delay Doppler symbols are converted into time frequency domain. Then we convert these symbols to the time domain and transmit it into the wireless channel. So at the receiver and the deprocessing of this operation at the transmitter happens, and we demodulate our symbols. Next slide. In OFDM, we start our processing from the right hand side of this presentation slide, where our symbols are mapped in the time frequency domain. Whereas in OTFS, we start from the left hand side, where symbols are mapped in the delay Doppler domain. So the conversion from delay Doppler domain to time frequency domain is like, for Doppler to time, we perform inverse Fourier transform, and for delay to frequency, we perform Fourier transform. So here one thing to observe, like for one symbol in delay Doppler domain is going to spread across the time frequency grid. So it has the influence over the whole grid. Similarly, if we see in the reverse direction from time frequency domain to delay Doppler domain, each symbol has impact over all the symbols in the delay Doppler domain. So after converting this delay Doppler domain into time frequency domain, we further convert it to time domain and then transmit it to the channel. So at the receiver end, to get this delay Doppler domain symbols, we first have to have complete time frequency grid. So what happens at the receiver end when we have this complete time frequency grid? So the channel gets average out. The defade effect is minimized when we convert it into the delay Doppler domain. So here OTFS gives advantage over OFDM and performs better in high Doppler scenario and or time varying channel scenario. Next slide. So here is one plot which shows the performance of OTFS over OFDM. This plot is generated for speed 500 km/h for carrier frequency of 2 GHz. So we can see that OTFS is performing way better than the OFDM, and it is resilient to high Doppler spread scenario. Next slide. OTFS provides a sparse channel model, so we need to estimate very less channel, and it is constant for a very long duration and require very less frequent channel estimation in case of time varying channel. It provides channel model which is both time as well as frequency selective, whereas in OFDM the channel is only frequency selective. We have seen that it is very efficient in high mobility scenario, and also it is flexible to integrate with the existing OFDM system. Next slide. There are other few parameters upon which a new waveform should be evaluated other than the Doppler spread and integration with the existing technology, that is low PAPR. High PAPR is also a very big challenge in OFDM system. So the new waveform should minimize the PAPR. It should be robust to the phase noise, provide high spectral efficiency, and should have low outer band emission. Next slide. There are few other candidate waveforms. Due to time constraint, I'm not going into the detail of these waveforms, like generalized frequency division multiplexing, GFDM, and universal filter multi-carrier, UFMC, but I'm going to provide a very short table comparing few of the parameters for these waveforms. Next slide, please. So in case of PAPR, all these four signals are the multi-carrier signals. All of this gives very high PAPR, but in case of OTFS, there are some technique has been introduced for the OTFS which reduces the PAPR in comparison with the OFDM. Next slide. Another parameter is spectral efficiency. In case of spectral efficiency, OFDM has medium spectral efficiency, where GFDM provide high spectral efficiency, and for study of spectral efficiency of OTFS is still open to work, and UFMC provides medium spectral efficiency. Next slide. All other new waveform provide has a higher complexity when compared to the existing OFDM system. Next slide, please. OFDM is not suitable for high mobility scenario. We have seen that. So is GFDM and UFMC. But OTFS provides very good performance in high mobility scenario. Next slide, please. So this is the summary of the table I have described. So this is from my side. Thank you.
Thank you, Ashna. So that was a wonderful presentation, and thank you for staying on time too. So definitely another exciting area where we definitely need more people coming on board and contributing to this effort. One second. Okay, sorry about that. So the OTFS represents a promising approach to addressing some of the key challenges facing wireless communications, high mobility, multipath propagation, interference, and so on. So by leveraging a interesting signal processing framework, this can provide many benefits, improve spectral efficiency, low latency, and so on. So definitely another exciting area. So please, if this area is of your interest and you like to contribute, please step forward, reach out to us. We'll be happy to get into more details and get you all tuned into what's going on. Okay, so having said that, let's go to the next speaker, Abhishek. I guess we kind of saved the best for the last, I guess. AI/ML and file layer is a pretty exciting area. So Abhishek Kumar Singh is working as a project executive officer in 5G plus 6G project and standardization project group at IIT Kanpur. He's a RAN 1 delegate and 3GPP contributing towards AI/ML for NR AR interface. His interests include AI/ML application for file layer enhancement, integrated sensing and communication, intelligent reflective surfaces, satellite-assisted terrestrial communication, and CSA enhancements. So Abhishek, exciting new area. Take it away. Thanks.
Yeah. Hello, everyone. Sir, am I audible?
Yes, you are.
Yeah. Thank you, sir, for such a kind introduction, and thanks TSDSI for giving me opportunity to give overview on a study on AML assisted physical layer communication for current release 18 and release 19 and beyond. So this presentation will be about introducing the audience to the application of AML assisted physical layer application in current release and for the upcoming releases. So next slide, please. Yeah. Now, before introducing the audience to how AML is going to assist, I would like to motivate the audience about why there is a requirement of AML for physical layer when we are already having such a better requirements that are there in 5G. So 4G to 5G transition was all about requirements of ultra reliable low latency, enhanced mobile broadband, and massive machine type communications. So that were being fulfilled by the conventional methods in physical layer. But when we are transitioning from 5G to 6G, so there will be some more objectives that need to be fulfilled, and these objectives will be like better utilization of available physical layer resources like bandwidth, power, time, space, which will require optimization of some of the conventional layer methods like reducing CSI feedback overhead, SRS overhead, other signaling overhead as being already discussed by the previous speakers. Also require better reference signal resource allocations. Better channel estimation techniques will be required. Also, we require better improvisation of positioning and beamforming. Other objective will be if we have these networks will be improved for sensing and integration of sensing and for communication. Then they will require common waveform designing, joint beamforming for sensing and communication, and also resource optimization. Apart from that, one more objective which requires application of AIML for physical layer is like if RIS is going to be integrated, then the intelligence that need to be provided to the RIS can be improved if the AIML is going to be there at the base station and at the UE side. So with all those objectives in mind, AIML is being introduced in current release 18 in RAN 1. Next slide, please. So AIML was first time introduced in current release 18 for the physical layer with 3 use cases. That is AIML for beamforming, AIML for positioning, and AIML for channel state information enhancement. So here I will be discussing, elaborating one use cases, and other will be of similar kind. Next slide, please. So AIML for channel state information. First, I will like to introduce what is the channel state information, why there is a requirement of that. So when we are talking about massive MIMO, the performance gain of that massive MIMO heavily depends upon the accuracy of the channel state information, which will be used for the beamforming. So this channel state information in case of downlink, as you can see in the figure, the architecture is like base station will send some reference signals which are like channel state information reference signal to the base to the UE through the downlink channel. UE is going to estimate the downlink channel, and then UE has to share that downlink information with the base station. So UE will perform the SVD and will calculate the downlink precoding matrix. That precoding matrix will be shared with the base station using the precoder matrix indicator, rank indicator, and channel state information indicator, quality indicator in case of conventional methods. But these information which are part of feedbacks becomes significantly huge, and conventional methods face some challenges. Next slide, please. So there are some challenges that are faced by the conventional methods, that are significant feedback overhead will be there when we are having the multi-user MIMO. Massive MIMO, in case of that, dimension of the channel estimated will be huge. High mobility scenarios where the channel will be changing over the time, then conventional methods will lag, and every time we have to send the channel state information. If the highly frequency selective fading is there, then CSI need to feedback for every sub band or every band that is can be there. Also, these conventional method are less accurate because of the use of approximation using the DFT matrix, and also because of the channel aging. Channel aging is the problem where the time of estimation of these channel precoded matrix by the UE and the application of that by the base station for the beamforming can be different, and over that time the channel can change, hence the accuracy of the CSI precoded matrix will be less. So with those challenges in mind, CSI AIML was introduced for the CSI enhancement. Next slide, please. So AIML was introduced for the CSI feedback with 3 architectures in mind. As you can see on the leftmost is one-sided AIML model, where AIML model was only introduced on the base station side, which is going to enhance or refine the received precoded matrix. It's kind of denoising that precoded matrix so that in case of multi-user MIMO or in case of single user MIMO, it can give us better performance than the conventional methods. Second one in the middle is two-sided AML model, which takes precoded matrix calculated by the UE as the input and going to compress that, and that will be sent as a feedback to the base station, and base station is going to recover that using the AIML decoder. So it's going to utilize the correlation that is present across the frequencies and across the time, and that was not being used by the conventional methods. The one on the right is where the raw channel matrix that is being estimated by the UE is taken directly as an input to AML encoder, and that will be shared with the base station. So one on the right is in discussion because when we are talking about the multi-user scenario, it can give better performance than the middle one. So these are the AML based CSI feedbacks that are in current release discussion. There are other two use cases of AIML in current release. Next slide, please. That is AIML for beamforming and AIML for positioning. So AIML for beamforming requires the selection of optimal beam, and that is using the CSRS or SSB as the input. Also, if the UE is moving, then prediction of that beam over the time or spatial. That can be solved using the AIML at the G node B for better beamforming. Also, AML for positioning, conventional methods are suboptimal because they heavily rely on the line of sight scenarios. So for cases where non-line of sight scenarios are there, in those cases, AML can be applied, and it can help us in better. It can help us in estimating the better position of the object. And also, if the UE is moving and high mobility scenarios are there, then AML can help us in better estimate of the positions. So these were three use cases that are there in current release 18 AIML for physical layer. Next slide, please. Yeah. Now, in terms of standardization point of view, if these use cases are need to be fulfilled, then there are some requirements. Those requirements are like, if different architectures are being used, then how to identify which architecture is suitable for which use case. Also, if model need to be trained over the time, then where to train that model. Should it be one-sided training, which should it be two-sided training? If the two-sided training is needed, then how to share the parameters? Should the whole model need to be transferred, or only the parameters need to be transferred? Also, is there any requirement of online or offline training? What will be the cutoff for that? Also, if model need to update, then how to fine tune that model? Also, for different scenarios like urban micro, urban macro, indoor, outdoor, should we require different scenario model for different scenarios, or different bandwidth configuration, different antennas configuration? So all these points are currently in discussion in current release 18. That is all for AIML for current release 18. Next slide will be talking about AIML for release 19. One more item that is possible to be introduced in AIML for release 19, that is AIML for reference signal allocation. Next slide, please. Yeah, so for reference signal resource allocation, like one I have seen, shown in the diagram, it can be applied for compressing the CSRS or reference signals that are going to be used for channel estimation. Like instead of full antenna ports using, we can compress the CSRS for less number of antenna or optimal number of antenna uses of the CSRS, and same can be recovered at the other side using the AIML technique. So with that, objective will be like reducing the amount of interference signals used, also optimal resource signals used, so that you don't lose any estimation of the channel or any other performance degrade, and also it helps us in better channel estimations. So next slide, please. Now, that is for release 19. As we are moving towards 20 and beyond, there are two more use cases that are already being discussed by the previous speakers. That is ISAC, integration of sensing and communication, and also IRS, intelligent reflective surface. So AIML will also be applied in order to assist those techniques for better communication performance. So I will be discussing each one of them slightly. Next slide, please. So AIML for integration of sensing and communication has various use cases. One of the use cases is like how to design a waveform which is optimal both for joint sensing and communication. So that will require the waveform. What should be the on-off time of that waveform? What should be the power allocated for joint sensing and communication? What should be the frequency hopping of that waveforms? And so that it can help us in sensing also and estimation also. So that is one objective in which AIML can be introduced at the G node B so that it can utilize the sensed data and it can change the parameter of the waveform so that the common objective of improving the data rates and better utilization of spectral efficiency can be recovered at the base station side in the network. Next slide, please. Other use case is like jointly beamforming for sensing and communication. So like we need a joint beamforming where one beamform will be required for the sensing, which requires the objective of wide beam so that in one shot we can have better estimation of the whole environment. And whereas the communication requires the beam to be very narrow so that we don't have interference with the nearest user. So this common objective need to be fulfilled by application of AIML at the G node B so that it done the joint beamforming at the required side of sensing and at the same time of required side of the beamforming. So these are two objectives use cases that I have discussed here. Other are also possible like resource allocation, interference cancellations, but keeping the time limit in mind, I have discussed here the two use cases. Next slide, please. Now I will be talking about AIML, how AIML can assist the reflective intelligence surface. So in RIS, the intelligence that is there in the RIS can be improved if the AIML can be applied and it can overcome the limitations that are there in the conventional methods. So RIS need to support multi-user scenario at the for multiple users. These users can have different profiles. They can be moving, they can be statics also. So how to jointly channel estimates these multiple users, so that can be fulfilled if the AIML model being installed at the UE side and at the base station side, and it can help us in better channel estimate for the multiple users. Also, if UE is moving, then conventional methods cannot have track of that positions of the users, and then the beamforming cannot be done over the time. So channel prediction of high mobility scenarios can be fulfilled by application of AIML at the G node B, and a G node B can provide that information to RIS controller, and then it can change that over the time for different users which are moving. Also optimal beamforming for multiple users. One use case, one requirement is like how much resource need to be allocated to each user which is very nearest may require least elements, which one which is very far require more elements, so that is one more requirement. Also RIS for ISAC will require RIS to be jointly for sensing and communication, then IML can assist that in helping RIS for ISAC and communication. Next slide, please. Yeah, so that is all from my side. I have tried to conclude the application of AIML for physical layer, and there are many other use cases, but keeping the time in mind, I have tried to summarize that. Thanks, everyone.
Sheikh, really appreciate it and appreciate you staying on time too, and definitely AI/ML is a pretty exciting area, and everybody is probably aware of what ChatGPT is also doing right now, right? I mean,
Yes.
see you could just see the potential. I feel that potential of AI/ML will just barely scratch the surface. So I want to take a moment to thank all the presenters. It was a very comprehensive overview of all the different subjects, and if you have noticed, all the subjects are kind of tied with each other, right? I mean, it started with reflecting surfaces, went to selfie network technology, network repeaters, but all of them have some AI/ML applications built in there, right? Even positioning framework. Waveform design is another exciting topic. So, definitely all these conversations are extremely important, and we want to sort of bring everything up to you, everything in front of you, so that you could look at it and see which area you are interested in, and so that you can figure out where you want to contribute. So in the remaining time, I want to let's go to the next slide, Asif. So we have a quick poll. It's a bunch of simple questions which we would really like you to get some feedback from your audience on in terms of your thinking along these for these questions. So for each poll question, I'll describe the question. You will have some 30 seconds to answer the question, and we'll show you what the poll results are. Okay. So let's go to the next slide. Let's start with the poll, actually. No, before we go to summer, let's do the poll. Is Asif online? Yeah. So this is the first question. So we just want to gauge from the audience, like, how familiar are you with this with the standardization process and release timeline? So how familiar are you with the GBP standardization process and release timeline? So let's start the timer now. We can stop the timer. Asif, can you show the results? Okay, so it looks like most of you are quite familiar, so which is somewhat familiar, which is good to hear. And so we definitely, at some point, one of the things that we want to do is to do a complete detailed workshop on 3GPP. Get into more details on exactly what 3GPP is all about, how do you contribute, and things like that. So that's something that kind of say, what's the space, right? So next, let's go to the next poll question. So we talked about a whole bunch of topics today. So hopefully you remember all the topics. So this question is related to kind of getting to the punchline, right? So if you belong to an organization, are you interested in making a contribution to 3GPP in any of these topics discussed today? That's a question. So so the two options, yes, if you're, it means that you're already have IPs that are related to that, and you like to talk to DSDSA about actually making a contribution. And no means like it's not relevant to you. Could be some other topic too, but that you can get back to us later. So Asif, let's start the timer now. Okay, I think hopefully everybody's voted. Let's stop the timer. Let's see the results. Wow, that's very good to hear. I mean, we have close to 185, 190 people. So looks like a lot of you are extremely eager to contribute, and this is music to our ears. So we'll definitely reach out to you and sort of look at the next steps. Thank you for answering. Let's go to the next poll. Okay, so this is more related, let's say that if you are not interested in directly contributing, making a contribution, but you definitely like to work with someone, right? It could be academia or some other organizations, right? Could be collaboration, maybe it could be even funding, we don't know, right? So if you're interested in working with someone else, right, you vote yes. If not, you can vote no. So Asif, let's start the timer here. Okay, let's stop the timer. Let's see the results. Wow. Okay, this is really good to hear. So thank you to everyone for enthusiastically participating in this poll. And so we definitely would like to follow up with you on how to take this forward, and we'll figure out the next steps going forward. So thank you again, and let's last but not the least, we have my good friend Samar coming on board. Let's go to the Next slide. I'm extremely happy to introduce Samar. He's going to give some concluding remarks. Dr. Samar Shailendra is a senior standards architect at Intel and leads standard delegate, the lead standards delegate in India and 3GPP SA6, which is really the application enablement critical communication section of 3GPP. He's also a visiting professor at IIIT Bangalore. Currently he's the co-chair of the TSDSI Roadmap Committee and vice chair of the TSDSI Study Group Networks. He's a very active participant in TSDSI. He keeps everybody going, and I don't know where he gets the time to do everything. He's always on calls and contributing at a very high level. So over to you, Samar.
Thank you, Guna. Thank you very much. First of all, I must tell you that the people who are present here are far more busy than I am. I know Professor Chaturvedi, Professor Buddhi Raja, all the guys who are contributing to 3GPP. And with all this 3GPP stuff coming up, we have this RAN meetings coming up next week. Then we have the plenaries, everything. Trust me, I know everybody else is much more busy, and I'm probably the most available guy among them. So credit to them, kudos to them, and wonderful workshop. I mean, I was glued to the sessions throughout this 1.5 to 2 hours, and a lot of information, a lot of stuff flowed in. And the best part is it was so lucidly and so well organized and presented that it was wonderful show. We had the 3GPP workshops earlier, micro workshops, where we presented the release 19 topics, the 3 topics. After that, we started with this series of workshops, where we deep dive on the technologies, the work which is happening across India in the academics, in the industry, and so on and so forth. And this is obviously the first in that series, which was focused on the physical layer technologies. So I really thank IIT Kanpur, Professor Chaturvedi, Professor Buddhi Raja, who orchestrated this entire workshop and brought it into the existence. Of course, special thanks to all the speakers, Abhishek, Jyotirmay, Ashna, Shyam, who introduced this topic. Wonderful topics, very close to my heart. Trust me, some of them has been very difficult for me all the time, but today it became very easy. But interestingly, the one which reminded me of Professor Subra Shekhar Das, who is not there. I'm not sure if he's joined online, about the OTFS. He has been talking about OTFS for quite some time, and I have discussed about it with him many times actually. But nevertheless, the other topics, intelligent reflective surface, which Professor Chaturvedi spoke about, very nice. I just on a lighter note, I called my son and asked him to listen to it. He is also a JEE aspirant, right? So I told him, look, a day might come when you won't be listening to him live, but listen to him. It's a privilege for you. The Selfie Architecture, I have been a personally big proponent of the same. So interesting stuff. I know it's probably the technology of future. And of course, all the other talks on network control repeaters, which Guna said reduces the cost significantly. The positioning, I think that's the heart of 6G going to be. The IoT, industrial IoT is highly relying on that. And AI/ML, that's horizontal. I mean, needless to say, every area of 3GPP is going to be impacted by it. I myself strive to learn a lot of reinforcement learning myself. So a lot of stuff, a lot of exciting stuff is coming up. Apart from that, this workshop has laid the foundation for gearing up the entire TSDSI and the intent ecosystems to contribute to the standards. We have been very heavily discussing with DoT and everyone so that we can increase the footprint of India into standards. And in fact, I'm very, I wasn't knowing actually that IIT Kanpur has got a lot of contributions happening and a lot of people involved into 3GPP ecosystem. So it's good to know. It's a interesting thing, and I would suggest and I would like that ITK mentors around all the other IITs. I know some other IITs are fairly active, so all of them should mentor out the other newer IITs, triple IITs, NITs to bring up a model how to contribute to 3GPP. It's not easy. It's a difficult task. But then if you methodologize, if you create a process around it, it becomes very interesting. And I say that standardization is like addiction. Once you are into it, you are into it. The TSDSI, along this or with all these micro workshops and a lot of others will be coming up in the future, will definitely like to engage more closely, because if people are not aware, they must know that TSDSI is the way for Indian companies to participate into 3GPP. That's why TSDSI becomes very important for standardization. We are the organizational partner of 3GPP, one of the organizational partner across 7 or 6 others. And the members of TSDSI gets the opportunity to contribute to 3GPP directly. That's the way it has to be. You have to become an individual member through TSDSI to 3GPP so that you can contribute there. So if you are really excited about it, which I saw through the polls, that a lot of people are involved in standardization work, technologies, etc., they must come to TSDSI, join 3GPP and contribute there. Of course, this was the start of the technical deep dive. I'm sure audience had a lot of questions for the panelists. They must have answered. If you still have more questions, please reach out to them directly. All their details are available. The recording of this workshop will also be available, because I think this is a good asset and resource which everybody should refer to. And going forward, we'll have some more workshops coming up. However, they are still in planning. So remain tuned. Watch out for us. We will see you again. And lastly, I want to thank all the organizers, speakers, IIT Kanpur for making this happen. And lastly, not the least, the TSDSI Marcom, Secretariat, Guna, IT team. Without them, this would not have been possible at all. So thank you very much. Thank you all for a great event. And thank you all the speakers once again. Over to you, Guna.
Thank you, Samar. I think appreciate the great concluding remarks. So I mean, another great workshop. I still see everybody hanging on towards the end, so it's good to see that. So you know, we will make announcements on the next workshop pretty soon. So look for you know, watch the space. We have a lot more things planned. So stay tuned and have a good day. Thanks for attending. Bye.
Probably, you must also add that this has set up the standards. Till now, I felt that 3GPP is the best standard setting organization, but today the speakers here have set up the standard by keeping everything on time.
Yeah, incredible. We're still under time, so it's a new record. So thanks IIT Kanpur. Really appreciate all the speakers. Yeah, good job.
Yeah,
Thank you so much.
Thank you.
Yeah.
Thank you.
Thanks, Professor Rohit. Thanks. Thank you.
Yeah.
Thank you.
Thank you, sir. Thanks.
Bye.
Thank you, everyone. I'm just closing the session.
Yeah.